Inequations. Equations, pretty much the same thing really, but within equations we get many possible values often, rather than equations where we generally just get an answer. Although quadratics you get two, and some of them you get multiple ones. But it's still the same idea. We're just trying to make whatever the pronumeral we're working with the subject of our inequation. But there is, of course, a key difference: the inequality sign itself. Now, we need to change it when we multiply or divide both sides by a negative number. Or the way I tend to think of it, if you change the sign, you change the sign. So if you change the inequality sign, then you change the sign of the number itself. So if you change the sign, you change the sign. The other one doesn't happen as often, but if you were to turn both sides of the inequality upside down, then that would flip the inequality sign as well. Well, not an exactly mind-blowing example, but I use it just to illustrate the plotting of the solution, the graphical solution. So we put it on the number line. 6 is not included, so we put a hollow circle to indicate the boundary is not included, and then an arrow to indicate which direction we're going. Now when I'm doing mine, I always put my arrow above the line so I don't lose the solution. Sometimes people will put it on the line itself and then you lose it depending on what colour ink you're using and things like that. I think it's just easier to put it just above the line, and then it's very clear what your solution is. The other key difference, I guess, with an inequation as opposed to an equation is we can have more than two sides. So this one here's got 3 sides, if you like. But that's all right, still the same sort of idea. I'm going to move 6, but I'm going to move it to both sides. So I get minus 4x is in between minus 4 and 8. Now I'll divide everything by negative 4, but if I change the sign, I change the sign. And that of course just looks ugly, so I rewrite it so it looks nice. There we go, minus 2 less than or equal to x less than or equal to 1. And if I was to put that on our number line, now those boundaries are included, so a solid circle, and I'm in between. Which now brings me to the correct, in inverted commas, translation, Mr. Simmons is very fussy, way of writing inequalities. Your algebraic solution should match, in other words, look like, the geometrical solution. It's a much nicer way of writing the answer. So if I have something like this, I would write it as x is greater than 5. It matches the picture. See, the arrow is pointing in the same direction as the inequality sign. So x is greater than 5. I wouldn't write it as 5 is less than x. Yeah, technically it's correct, but it's not a good way of writing it because what we're trying to find, we make the subject of the equation, or inequation in this case, and we tend to put the subject on the left hand side. So x is greater than 5 is better than 5 is less than x. So if I'm in between, again I make it look like the solution. 4 and 6 are on either side of the x, and one's less than and one's less than or equal to. I would not write it like that. It doesn't look good. You don't see 6 before 4 on the number line. Make it look like the picture. And I've seen people do that, try and write it as two things. That's just plain wrong. It can't be x is greater than 4 or x is less than or equal to 6. Otherwise that would cover every number. It's actually an and case if I was going to write it as 2, but I wouldn't write it as 2. But it would be and rather than or. Ones where it's either side, this is the or case. So x is less than or equal to 4 or x is greater than or equal to 6. Again, it looks like the picture. So I've got a bit going to the left and I've got a bit going to the right. I wouldn't write it the other way around. It just doesn't look right. I've even seen people try to do something like that. And again, that's just plain wrong. You know, don't try and do that one. This is the or case, so because it's or, we write it as two separate things. That brings me to quadratic inequations then, rather than linear ones. Something like this. I'll factorise it just like I would an equation, but this is where it becomes different. See, if it was an equation, I would have said either x plus 6 is equal to 0 or x minus 1 is equal to 0. Well, I can't do that for this one. I can't say either x plus 6 is less than 0 or x minus 1 is less than 0. One of those cases would be incorrect. Think about the picture. That's why we spend so much time looking at basic curves and things like that. Imagine the picture and it makes life a lot easier. What do I have? There's my parabola. I've got x-intercepts at -6 and 1, it's concave up. I'm not really concerned about the vertex or the y-intercept because my equation only is dealing with x values. I don't really need to know about the y values here. So they're the important ones, the -6 and the 1. But what is it saying? Well, it's basically saying, when is this negative? When is it below the axis? Well, it's this piece of the curve, but again, I'm only concerned with the x values. So really, I just want the domain of that function when the range is restricted to y is less than 0. Well, that would be in between -6 and 1. There's my solution. This one here. Personally, I hate factorising negative quadratics. I don't know what it is, I just hate it. So I'm going to multiply everything by -1. But if I change the sign, I change the sign. Factorise it. Let's draw my parabola. This time they're included, the boundary. But this time I'm saying, when is it above the x-axis? It'd be on the outside. Now, the thing with quadratic inequalities, it's either going to be one of those two cases. The x value is either going to be in between those two x-intercepts or on the outside. It's the only two things it could be. Of course, what you can do, and this is often a very good way of solving inequations, is don't solve the inequation, solve the equation. Find those, what we call critical points, the solutions, and then you can just test values to work out where you are on the number line. Absolute value inequations then, something like this. X plus 5, the absolute value of it is less than 2. Remember the definition of the absolute value function. And this is what I was talking about the other day. The definition becomes really important. That was our definition. So I'm going to say either x plus 5 is less than 2 or the negative of x plus 5 is less than 2. And then solve each of those and I get my answer. But I want when that's both true, so I must be in between the -3 and the -7. For this one, either the 3x plus 2 is greater than or equal to 1 or the negative of that is greater than or equal to 1. Solve each of those. This time I've got one going that way. Well, this is an OR case. So if they intersect each other, it's going to be the AND case. If they don't, it's the OR case. There's my solution. But here's an alternative way of doing it. I've got to be honest, I don't do it this way myself, but it's a valid way of doing it. I can turn it into a quadratic inequation. Okay, so here was the inequation. Absolute value of x plus 5 is less than 2. If I square both sides, right, squares are always positive, just like the absolute value is always positive. I'll get x plus 5 squared is less than 4. Now I'll go and solve that quadratic inequation. So move everything over, factorise it. You can see we're going to get the same values we got before, -7 and -3 were the two key points. And then for this one I end up in between. I get the same answer. The other one was this one. Absolute value of 3x plus 2 is greater than or equal to 1. Okay, let's square both sides. I go down. Again, I come up with those same two critical points, -1, -1/3. And if I was to solve that one, I'd be either side. It's an alternative way of doing it. Now comes the really interesting one. Pronumerals in the denominator, and there's probably about, I don't know, at least 5 different ways I can think of approaching this problem. Let's start with a very simple one. 1 over x is greater than or equal to 3. And I know I've got an issue, because the bottom of the fraction can't equal 0. This will locate the first critical point. So I know x can't equal 0. That cannot be a solution. But now I'll just solve it like an equation. So that idea of saying, don't solve the inequation, solve the equation. They're easier to solve. If I solve 1 over x equals 3, I get x equals 1/3. I now have my two critical points to investigate. Plot them on the number line, but remember, 0 is not included, 1/3 is, because it was greater than or equal to. And then I just got to test regions. Okay, -1, I wouldn't necessarily write this down, you're probably doing it in your head, but I'll test x equals -1. If I sub that in, is -1 greater than or equal to 3? No, it's not. So that's not part of my solution. Well, what about in the middle? Let's pick a point in the middle. 1/4. Well, there's 1 1/4. Well, that's 4. Is 4 bigger than or equal to 3? Well, yes it is. So I know I'm in that section. And then if I check on the other side, x equals 1. Is 1 greater than 3? Well, no, it's not. There's my answer. So x is in between 0 and 1/3, but including the 1/3, not including the 0. This is what's called the critical points method. Let's have a look at this one. 2 over x plus 3. So all we simply do is, what makes the denominator equal to 0? X plus 3. That gets my first critical point. I'll just go and solve it like an equation, simple little equation to solve, and I get minus 13 on 5. There's my 2 key points. Neither of them are included this time. I just got to test to see where it is. Pick a number over on the left-hand side. Yes, that one works. What about in between? No, but on the right-hand side it does work. I've got my answer. You could also turn that sort of an equation to a quadratic as well. And a lot of people like this method. I'm not one of them, but a lot of people like this method. 1 over x is greater than or equal to 3. So what we do is we multiply by the denominator squared. You see, if I just multiplied both sides by x, I've got a problem because I don't know. Is x a negative number or is x a positive number? Because if it's negative, I've got to change the sign. But if it's positive, I leave the sign alone. So I've got an issue. That's why we multiply by x squared, because we know that's a positive number. The sign doesn't change. So if I multiply both sides by x squared, I get x is greater than or equal to 3x squared, and I can go and solve that quadratic equation. And I come up with the answer we got before. But don't forget the domain issue if you're using this. See, this quadratic inequation includes x equals 0, but we know it can't have x equals 0 because of the bottom of the fraction issue. And when people use this method, that's the thing they often forget and leave their solution like that. X can't equal 0. So a better way of writing that solution is simply like that. The other one, if I was to multiply by the square, I'll multiply both sides by x plus 3 squared. Now, if you are using this method, for goodness sake, do not expand out. That's crazy, because when I move it to the other side, they've automatically got a common factor of x plus 3. We're going to have to factorise anyway. Why expand out? Only have to factorise back again. So I'll just pull out that common factor of x plus 3, and I get 5x plus 13. And there's my solution to that quadratic equation. But of course, x can't equal negative 3. In this case, that's not an issue, because it wasn't a solution anyway. So I have my answer. This is the most popular method of solving it. However, the first way I showed you is the most successful way. More people make mistakes with this method than they do the first methods. That's what I'm saying. Use the first method. Okay. 5A.